probability is that there's something we try not to comprehend about the universe. Join us as we dive profoundly into how new ultra-deep pictures from James Webb just affirmed there is something truly amiss with how we might interpret the universe. Our universe began with a bang. The huge explosion of energy, mass, and space streaked into reality all inside a momentary moment. Then the youthful universe was framed, an expanding, roiling plasma stock of matter and antimatter particles that jumped into reality just to obliterate each other upon contact. Left to their own devices, the matter and antimatter inside this plasma ought to have consumed each other altogether. However, researchers believe that some unexplored world irregularity empowered more matter than antimatter to be produced, saving the universe from immediate implosion. Gravity compacted the plasma pockets, pressing and warming the matter so that sound waves traveling just over a portion of the speed of light, called baryon acoustic oscillations, undulated across their surface. Meanwhile, the high-energy density of the early universe's compact contents stretched spacetime, pulling a little part of this matter securely from the fry. As the universe swelled like an inflatable, the standard story goes that ordinary matter, which interacts with light, solidified around clusters of invisible dark matter to form the first galaxies, connected together by a huge cosmic web. At first, as the universe's substance spread out, its energy density and, subsequently, its growth rate diminished. However, around 5 billion years ago, galaxies began to retreat once more at an increasingly faster rate. The reason was another invisible and strange substance known as dark energy. The simplest and most popular explanation for dark energy is that it is a cosmological constant, an inflationary energy that is the same everywhere and at every moment, woven into the expanding fabric of spacetime. Einstein named it lambda in his theory of general relativity. As our universe developed, its general matter density dropped while the dark energy density remained the same, steadily making it the greatest contributor to its overall expansion. Added together, the energy densities of ordinary matter, dark energy, and energy from light set the upper speed limit of the universe's expansion. They are also key ingredients in the lambda cold dark matter, LCDM, model of cosmology, which maps the development of the universe and predicts its end with matter eventually spreading. So far it encounters a heat death called the Big Freeze. Many of the model's predictions have been shown to be highly accurate, yet here's where the issues start. Despite much searching, astronomers do not know what dark matter or dark energy are. As Ofer Lahav, a professor of astronomy at University College London who is involved in galaxy surveys of dark energy, said, "A great many people agree that the universe's current composition is 5% ordinary matter, 25% cold dark matter, and 70% dark energy. The embarrassing reality is we don't understand the last two of them. However, a considerably greater threat to the LCDM model has emerged. Depending on the method used, astrophysicists find the universe appears to be expanding at different rates, a discrepancy known as the Hubble tension. Techniques that peer into the early universe show it expanding significantly faster than LCDM predicts. Those techniques have been reviewed and confirmed by countless observations. Consequently, as Nobel Prize-winning astrophysicist Adam Rees, who led the team that made the new James Webb measurement, said, "The only reason I can understand at this point for them to differ is that the model we have between them is perhaps missing something. Measuring the universe's expansion takes more than a radar gun. The primary method to measure this expansion looks at the so-called cosmic microwave background, CMB, a remnant of the universe's first light produced just 380,000 years after the Big Bang. The imprint should be visible across the whole sky, and it was intended to find a Hubble constant with less than 1% uncertainty by the European Space Agency's Planck satellite between 2009 and 2013. In this cosmic baby picture, the universe is generally uniform, but hotter and colder patches, where matter is more or less dense, reveal where baryon acoustic oscillations caused it to clump as the universe exploded outward. This soap bubble structure expanded into the cosmic web, an intricate network of strands along whose intersections galaxies would be born. By studying these waves with the Planck satellite, cosmologists derived the amounts of ordinary matter and dark matter and a value for the cosmological constant or dark energy, fitting them into the standard model, resulting in a Hubble constant of about 67 kilometers per second per megaparsec. We should pause on this number for a moment. If a galaxy is a distance of 1 megaparsec away from us, it would recede from us and us from it at 67 kilometers per second. At 20 megaparsecs, this recession grows to 1,340 kilometers per second and continues to grow dramatically from that point onward. If a galaxy is any farther than 4,175 megaparsecs away, it will recede from us faster than the speed of light. A second method to find this expansion rate uses pulsating stars called Cepheid variables, dying stars with helium gas outer layers that expand and contract as they absorb and emit the star's radiation, causing them to periodically blink like distant signal lights. In 1912, astronomer Henrietta Swan-Leavitt found that the brighter a Cepheid was, the slower it would blink, enabling astronomers to measure a star's absolute brightness and, therefore, check its distance. It was a milestone discovery that turned Cepheids into abundant standard candles for measuring the universe's scale. By stitching together observations of pulsating Cepheids, astronomers can build cosmic distance ladders, with each rung taking them further back into the past. It's one of the most reliable methods that astronomers have today for estimating distances. To build a distance ladder, cosmologists start with nearby Cepheids and cross-check their distance based on their pulsating light to that found by calculation. Wendy Friedman, an astrophysicist at the University of Chicago, said the next rungs are added using Cepheid readings alone. Then cosmologists look at the distances of the stars and supernovae on each rung and compare how much their light has been redshifted, stretched to longer, redder frequencies as the universe expands. This provides an accurate measurement of the Hubble constant. In 2019, the method was used by Rees and his teammates, who observed one of the Milky Way's nearest neighbors, the Large Magellanic Cloud, with the Hubble Space Telescope. Their result was striking: an incredibly high expansion rate of 74 kilometers per second per megaparsec compared to the Planck measurement. However, Hubble lacked the necessary accuracy for the dense regions of space the team was studying, causing some distant Cepheids to blend into neighboring stars, prompting cosmologists to argue that the result, while stunning, might have come from a measurement error. So, when James Webb launched in December 2021, it was poised to either resolve the discrepancy or cement it. At 6.5 meters wide, Webb's mirror is right 3 times the size of Hubble's, which is only 2.4 meters wide. Not only can James Webb detect objects 3 times fainter than Hubble can, but it is also much more sensitive in the infrared range, allowing it to observe a broader spectrum of frequencies. By examining Cepheids measured by James Webb in the galaxy NGC 4258, along with Type Ia supernovae, another standard candle since they all explode at the same absolute brightness, Rees and his team arrived at an almost identical result: 73 kilometers per second per megaparsec. Different measurements, including one made by Friedman with the Hubble Space Telescope on the rapid light curves of the most luminous type of red giant stars and another with light bent by the gravity of massive galaxies, returned individual results of 69.6 and 66.6 kilometers per second per megaparsec. Another result using light bending also gave a value of 73 kilometers per second per megaparsec. For theoretical physics, KITP, in California only caused more frustration, as the late Vera Rubin, who found evidence for dark matter, said at the time, "No one wanted to give up their toy. Everyone involved was so strongly invested in their own results and in the belief that their observations and measurements were done correctly that it left people grappling with how to explain it." In February 2023, with James Webb and another independent Cepheid distance ladder result confirming the Hubble tension, cosmologists are left with 3 potential explanations: measurement errors, new physics, or some combination of the two. Kai explained that most of the data supports new physics. The simplest and most popular theory is that dark energy behaves differently today than it did in the early universe. If dark energy was strong at one time and then faded away, it would make the universe appear smaller when we look back to the early universe, making the expansion rate seem faster today. Other explanations include the possibility that there are 2 types of dark energy or that dark matter interacts with light, but these explanations introduce complexities that cosmologists are wary of. Without further information, dark energy and dark matter aren't the only mysteries James Webb is helping to solve. When it launched, it was tasked with looking further back in time than any telescope before it. James Webb's revolutionary new imaging technology allowed it to see galaxies formed only 300 million years after the Big Bang. However, while examining the universe's origins, astronomers saw that these early-stage galaxies are much larger and more advanced than the standard model predicts. Early galaxies should have been full of young, hot stars forming at breakneck speed, yet James Webb showed that many of them were teeming with heavy elements from earlier generations of stars and already developing protruding centers of very massive black holes. James Webb's observations have intensified the debate in cosmology by providing precise data that confirms existing discrepancies and reveals surprising insights about early galaxies. Resolving the Hubble tension and understanding these early galaxies may require new physics or a significant revision of the standard cosmological model. The quest for these answers is one of the most exciting frontiers in modern astronomy. James Webb Space Telescope, JWST, has not only revolutionized our understanding of early galaxies, but has also opened new avenues for exploring fundamental questions in cosmology. Its infrared capabilities allow it to peer deeper into the universe than ever before, capturing light from some of the earliest galaxies formed just 300 million years after the Big Bang. These observations have challenged traditional notions about galaxy formation, suggesting that early galaxies were not merely simple youthful structures but were surprisingly mature, containing heavy elements and harboring supermassive black holes at their centers. This discrepancy between theory and observation raises crucial questions about the processes driving galaxy evolution in the early universe. It hints at potentially faster and more efficient processes than previously thought, leading to the formation of galaxies with unexpectedly complex structures soon after the Big Bang. Furthermore, JWST's discoveries have exacerbated the long-standing mystery surrounding dark matter and dark energy. These elusive components, which constitute the majority of the universe's substance, remain poorly understood. Dark matter, which interacts gravitationally but not electromagnetically, plays a critical role in shaping the large-scale structure of the universe, including the formation of galaxies and galaxy clusters. Despite extensive efforts, its exact nature and composition remain elusive, prompting ongoing searches through direct and indirect detection methods. On the other hand, dark energy, responsible for the accelerated expansion of the universe, presents an even more puzzling challenge. The standard cosmological model treats dark energy as a cosmological constant, uniform in its properties throughout spacetime. However, discrepancies such as the Hubble tension suggest that dark energy's behavior may not be so uniform. Alternative theories propose dynamic forms of dark energy that evolve over cosmic time, potentially affecting the universe's expansion rate differently at various epochs. Resolving these mysteries requires not only advanced observational capabilities like those of JWST, but also theoretical frameworks that can accommodate new data without discarding the achievements of the current model. Astrophysicists and cosmologists are exploring various hypotheses, from modified gravity theories to exotic particles and interactions beyond the standard model of particle physics. The implications of JWST's discoveries extend beyond cosmology into broader astrophysical questions, including the origins of life-supporting planets and the conditions necessary for complex chemistry to emerge in the universe. By studying distant galaxies and their environments, astronomers hope to gain insights into the conditions under which Earth-like planets might form and evolve around other stars, offering clues to the prevalence and diversity of life in the universe. Looking forward, JWST promises to continue pushing the boundaries of our knowledge, its exceptional sensitivity and resolution enabling scientists to probe the atmospheres of exoplanets, map the properties of distant galaxies in stunning detail, and test the earliest epochs of cosmic history with unparalleled accuracy. These efforts will not only expand our understanding of the universe's past, but also pave the way for groundbreaking discoveries that could reshape our comprehension of physics, cosmology, and our place in the cosmos. As JWST embarks on its operational phase, scientists eagerly anticipate new insights into the universe's most profound mysteries. Whether it's unraveling the nature of dark matter and dark energy, understanding galaxy formation and evolution, or exploring the potential for life beyond Earth, JWST is poised to transform our understanding of the universe in ways that were once unimaginable. In conclusion, the integration of cutting-edge technology, theoretical advancements, and rigorous observation promises an exciting era in cosmology and astronomy. JWST's contributions are set to be pivotal, offering a clearer view into the universe's earliest moments while testing and refining our fundamental theories of its structure and evolution. As we embark on this journey of discovery, the mysteries of the universe await investigation, and JWST stands at the forefront, ready to unveil the secrets of our cosmic origins and destiny.